As technology advances, the path from design concept to product creation is becoming more blurred. Advanced tools like Fusion 360 allow you to tackle ideation, digital design creation, and validation through simulation, as well as manufacturing, all in one place. Now you have the freedom to explore form and function digitally like never before. Through this course, we'll explore the aspects of designing and creating a complex search and rescue drone, giving you a deeper look into the planning and design phase of a complex electromechanical device. After completing a series of lectures and exercises using Autodesk Fusion 360 software, you'll be able to identify and select components for a quadcopter design, explore ideas inside the confines of design criteria, create a complex design with advanced CAD tools, conceptualize a product, explore generative type shapes, and produce realistic rendered images and video. There's a lot to do, so let's get started.
In this course, we'll use Fusion 360, a cloud-based 3D CAD/CAM tool for product development that combines industrial, mechanical design, collaboration, and machining. Fusion 360 is available for both PC and Mac users, and it enables fast and easy exploration of design ideas with an integrated concept-to-manufacturing platform. Best of all, it's free for educators, students, and institutions. To access and download the software, go to autodesk.com/fusion. Once there, select Student from the pull-down menu. From there, you'll be asked to create an Autodesk account or sign into an existing Autodesk account. Once you're logged in and registered, you can download and install Fusion 360 like any other software.
Fusion 360 User Interface. After completing this lesson, you'll be able to identify legacy, preview and updated user interface elements, and use the new Fusion 360 user interface. If you've been a Fusion user for a while, you may have noticed the changes in the user interface, from the legacy UI to the preview and now to the most current release. In this video, we're going to take a look at all of those and see how it changes the workflow. First, let's focus on the icons. The change from the preview UI to the most current has mainly been an update to the icons. There is some added functionality, but this shouldn't affect the location of any of your tools. But let's also take a look at the legacy UI and how things have changed in that workflow. So the preview UI has been out for a while, but if you've been using the legacy UI, it's going to be important for us to identify those differences. First of which is the access of the tools. In the new UI, we have this tabbed interface on the ribbon, while in the legacy UI, you have to navigate between a model, a patch, and a sheet metal workspace. So this difference in access to tools has been the biggest change in the workflow. You still create sketches the same, you still have the same access to your tools, but your sketch tools, for example, are going to be contextual. Your sketch palette looks a little bit different because all of the constraints have been now moved up to a toolbar, where before they were located in the sketch palette. So this shouldn't affect the actual modeling process, but only change the way you access your tools. For example, if you're used to starting a sketch by activating a sketch tool first, you can still do that with shortcut keys or the marking menu. So notice that we still have our sketch tools. They're located under a Create drop-down, and we have a sketch location on the ribbon that's located inside of our design workspace. So again, same tools, just slightly different access. Next, let's talk about some of the other workspaces. The Render workspace has received an update, but again, this is mostly in terms of the icons. Let's take a look now at the Animation workspace. And again, the functionality is the same, however the icons have slightly changed. And again, this is to keep them common across the board. Now, let's take a look at the Simulation workspace. This should look very familiar when starting a new simulation. You pick your study, and then you have access to your tools. In the legacy UI, again, all the tools are the same, however the icons have changed. So this again should not affect the way that you access things, with the exception of viewing the results. In some versions of the user interface, we might have seen a tab on the ribbon that allowed us to access the results. However, in the new UI, we now have a results button that brings up all results tools, and when we're done looking at the results, we simply finish. Now let's take a look at the Manufacture workspace. If you've been around Fusion long enough, this used to be called the CAM workspace. There have been some big updates that happened in this manufacturer workspace over the past year. And also, the user interface does look different depending on if you're using manufacturing extensions or if you're simply using the manufacturer workspace. It's always a good idea to check the preview functionality as well as the extensions that are available to see if any of these are needed for your workflow. Next, let's take a look at drawings. I'm not going to compare the new UI to the legacy UI in terms of drawings. Again, the functionality has stayed the same. However, the icons have been updated. You'll see here we still have access to the same drawing views and the annotation notes as we did before in the legacy UI. Back in the modeling environment, I want to talk about one more thing that has changed, and that's changed between the preview user interface to the new user interface. We no longer have a light bulb icon in our browser next to things that we want to change the visibility of. We now have an eye icon, and when we select the eye icon, it'll be grayed out with a slash through it telling us that these objects are hidden. However, when we activate it, the slash will disappear and the transparency or opacity of this will also change. So hopefully that's been helpful in allowing you to see the legacy user interface as well as the preview and the most current release user interface. In this lecture, we cover all aspects of drone UAV design, from planning, component selection, fabrication, and flying. Unmanned aerial vehicles or UAVs can be piloted by somebody on the ground or pre-programmed to follow a route or perform a specific task. A UAV can come in all shapes and sizes. In this lecture, we specifically focus on multi-rotors. Multi-rotors are categorized by the number of propellers. This drone design focused on in the course is a quadcopter or UAV with 4 propellers. A UAV can have any number and orientation. We focus on quad, hex, and octocopters and their applications. Quadcopters range in size from nano, that can be the size of your finger, to units that are several feet across. Their intended application dictates the size to a certain extent. Smaller drones are used for indoor hobby flight, while larger ones have specific functions. Somewhere in the middle, there are a large range of sizes that are used for various reasons, from FPV or first-person view quadcopter racing drones to GPS camera tracking drones and the newly popular backpack drones. Quads are probably the most popular style out there, and you've likely seen or flown one of these already. Going a step further, hex and octocopters, you add the ability to carry more weight and have a bit of redundancy in case of a motor failure. If a motor fails on a quadcopter, gravity wins. On a hex or an octocopter, you can still fly and land safely in most cases, protecting whatever precious cargo is being transported. This could be a burrito or life-saving medical supplies. By far the biggest application, other than just hobby flying, is in aerial photography. This could be a selfie drone or a rescue drone like the one we're creating. Camera drones are being used for 3D mapping, construction, search and rescue, action sports, agriculture, military, security, and even real estate. Basically any reason you would need an eye in the sky. Cameras can be anything from an octocopter carrying a DSLR camera to a quadcopter carrying a thermal imaging camera. Design and construction teams are quickly discovering the value that drone mapping brings to all stages of a construction project, including initial site survey and design, volume and elevation measurements, comparisons, and quality assurance. In a fraction of the time it takes to conduct a ground-based survey, a drone can automatically fly and capture imagery of a project site that can then be processed into highly accurate point clouds compatible with building information modeling or BIM software. Industrial designer and visual artist Eli Delia has taken drone design to the extreme level with Game of Drones. The drone sports company is creating a worldwide platform for beginners and experts alike to compete in drone competitions and sports leagues through groundbreaking drone hardware, software, and the toughest drone airframe. Eli is on the forefront of drone design, developing the next generation of UAVs for aerial combat to industrial and agriculture use, and even search and rescue training operations. Oftentimes, technology is driven by innovative students at colleges and universities, and design projects or challenges can be a breeding ground for innovation. This such innovation environment is exactly where the inspiration for our course came from. Japanese duo Yuki Akasawara and Ryo Komedo, aka Team ROK, and their innovative X-Fane design was born out of tragedy. In the wake of natural disasters in Japan, Yuki set out to create a style of post-disaster search drone. His innovative approach to design inspired us to see where we could take it next. In addition to Yuki and his design project, universities around the world are paying close attention to drones and utilizing them throughout their curriculum. One such university is Virginia Tech. Virginia Tech has invested in an outdoor drone cage that allows students and faculty to explore the next generation of drones without worrying about the confines of FAA safety regulations. This drone playground is 300 feet by 120 feet and 80 feet tall. This means things like swarms of drones working together can be realized without the risks associated with testing these drones in the open world. There's almost an endless line of stories of innovative students realizing new and unique ways to utilize this technology. And the great news is that it's literally at the fingertips of everyone. The last thing that we need to mention before we start designing has to do with legality. If you plan on actually building and flying your own drone, it's important to check with your local regulations. Best bet is to check your local regulations and the FAA website. In this design criteria lesson, we'll be talking about our design specifications. After completing this lesson, you'll be able to understand design requirements, apply critical thinking, and make informed design decisions. A design criteria is an explicit set of goals that a project must achieve in order to be successful. If you're designing a quadcopter like we are, or if you're designing any other product, you're going to have a list of criteria that you need to match. Now for our case, we're going to be creating a post-disaster search RPA, or remote piloted aircraft. Now this is the most important thing that we need to fit into. We need to have a vehicle that can go up into the air and view areas that are hard for us to get to. The next thing that we need to fit is ease of transport. That's going to be very important to us when we're creating something that can get into these locations where potentially there's a natural disaster, but it's hard for a human to get into these areas to search for people. So the ease of transport is going to be important because you're not going to want to hike to remote locations or get into these hard to access areas while carrying a large case with you. And lastly, we want to make sure that we have a long flight time. We're going to do everything that we can to optimize our design to increase that flight time. When we talk about our post-disaster search requirements, first and foremost, we need to make sure that we have a live camera feed. We're going to be designing our device to have a live camera color feed, and we have direct control over the tilt of that camera. So we want to be able to hover and look directly down, or we want to be able to have the camera forward as we fly so we can see where we're going and also look into different areas. The next thing that we want to design for is protected components. Because we are looking at a post-disaster drone, we might have down tree limbs, or we might have to fly into buildings where there is potential debris. We want to make sure that we do our best to protect all the components, the propellers and motors, as well as all the electronics and batteries. This is going to be important because we don't want to instantly crash the vehicle and have to recover it or repair it if we run into a wall or a tree limb as we're trying to fly into an area. We want to make this device fast and maneuverable. Now it's going to be important that we have a long flight time, but it's also going to be important that we can get up into the air quickly and that we can get into areas quickly as well. And lastly, we want to make sure that we have the ability to customize. Now currently we're planning for a color camera that we can tilt, but we might also want to include a thermal imaging camera. We might want to add GPS location so that we know exactly where it is, whether it crashes or whether we're just looking over areas that might be hard to see on a map, but we can get an exact GPS location. When we talk about our ease of transport requirements, we want to make sure that the overall size of our device is as minimal as possible. Now some of this is going to be driven by components, obviously. We have a certain list of components that we need to include, including the batteries. We know the props that we want to use and the size of the motor, and we'll talk about all those specifics a little bit later. But those are going to drive the overall size of our device. So knowing that the size of the motors, knowing the size of the props, knowing the batteries and all the other components, it's really going to drive the overall shape. But we know that we can keep it as small as possible while fitting into all those different requirements. One thing that is a big variable is the height of our device. We want to keep it as low profile as possible. A lot of the camera drones you see on the market are relatively tall because they have a camera hanging below them and they have stabilization on the camera, and they have various other components. Now this is done to keep the weight at a certain location in relation to the props, and again we'll talk about all that when we plan out our components. But we're going to do our best to keep the size as small as possible and the height as low as possible. Another thing that we want to do to make it easy to transport is keep it fully assembled. There are a lot of devices on the market that have to be assembled once you get them to your location. Because we are marketing or we're going toward a post-disaster drone, we want to make it easy to not only carry it to your location, but also to get it up in the air as quick as possible. Now this means that we don't want the people to have to put props on the device. We don't want to have to assemble all the different arms of the device. So we want to have it fully assembled so that it's very quick and easy to get it up in the air. We also want to, again, protect components. It goes back to the disaster search drone, but again, it helps with ease of transport. If everything is a nice protected package, we don't have to worry as much about putting it in a case or putting it in a backpack because we know everything is protected. And lastly, I have backpack drone. Now this is sort of a category that's popular now because there are plenty of drones on the market that can fold up and fit into a backpack. So we're going to minimize the size, keep it as low as possible, so that we can get it into roughly the size of a backpack. Next we want to talk about the long flight time requirements. We're going to start out planning for a minimum of 15 minutes of flight time, and we're going to explore various options to see how we can increase that flight time. It's going to be important that not only it's easy to get to our location and it's quick to get up in the air, but that we can stay up in the air and search for as long as possible. The next thing that we want in terms of our flight time is a good thrust ratio. Now a thrust ratio is the available thrust in relation to the mass of the vehicle. So for example, if we plan everything out so that we have a maximum of 2,000 gram force of thrust on a 1,000 gram vehicle, we have a 2-to-1 thrust ratio. For fast racing drones or acrobatic drones, you're typically going to see an 8-to-1 or a 10-to-1 ratio. Now we're not going to be going that extreme, but we want to make sure that we have at least a 2.5-to-1 thrust ratio, if not better. The higher that ratio, the quicker it can maneuver, but generally you're going to be drawing more current and you're going to reduce your flight time. So we're going to have to explore our options, and there's going to be some give and take to plan out what our maximum flight time while still keeping it agile enough to get to our areas quickly and maneuver into tight spots. We also want the ability to configure. Now what I mean by configure is be able to change out batteries and not just add new charged batteries, but maybe add a 4-cell battery instead of a 3-cell to increase the voltage. Maybe add longer batteries so that we have a larger amperage capacity. So there are various options that we can explore to configure the batteries and change the flight time. All of these different things will affect not only the flight time, but how much we can add to it in terms of cameras or additional components, and how well it's going to maneuver. So everything is going to be a give and take, whether it's in flight time or size or maneuverability, and these are all things that we're going to take into account when we start planning out our configurations. In this design criteria lesson, we're going to start to talk about our component selection. After completing this lesson, you'll be able to understand multi-rotor component basics. So first we want to talk about the basic parts of a multi-rotor. When I say multi-rotor, it's a general category of a multiple rotor flying device. So in most cases, you're going to talk about a quadcopter, which is what we're designing and has 4 motors. Now some cases you might have a tricopter, which has 3, or a hex or an octocopter or some other configuration. Now we've already talked about these in our introduction, but in general, all of these fall into the category of a multi-rotor, and they're all going to have the same equipment. Now in our case, the first thing is going to be a frame or a body that holds all of the things together so that we can fly it. Now that's the entire point of our course, is to design and engineer, manufacture our body so that we can have a custom device, a custom quadcopter that we can use for our intended purpose. Now you can buy a lot of off-the-shelf frames and build your own, and I will actually suggest during the course to buy some of these off-the-shelf racing drone frames to do as a test platform as we figure out all the components and the controls. The next thing is going to be the motors and the propellers. Now there are a lot of variables here, and we're going to talk about some basics to understand, and we're going to talk about some specifics when planning out a build. Now the entire point of our course is to design a 3D printed body for a disaster relief drone or a disaster search drone. But we want to make sure that you have all of the information to not only do that portion of the course, but to also plan out your own build. Because that's the entire point here, is to understand the design process, and here is specifically the design process as it applies to designing a quadcopter. So the motors and propellers, a lot of variables, we're going to talk about those in generalities, and then we're going to talk about specifics and calculations. Batteries, again, also lots of variables when you start to plan out a build with batteries. We'll talk about what the numbers on a battery mean. We'll talk about how to plan them into your build and how changes in the batteries will affect things. The flight controller. Again, when you're talking about multi-rotors or quadcopters specifically, there is no shortage of flight controllers out there. We have a specific one we're using because of its small size, but I'll talk about some others in general and what different options you might see when you start to plan out a build. An ESC, or electronic speed controller, is another important part of this type of build. It's going to take the information from the flight controller and it's going to convert it into something that the motor needs. The motors that we're using are going to be brushless motors, and they need a specific type of signal in order to turn and spin and be useful. The next thing is a PDB, or a power distribution board. Now these aren't generally needed on all types of multi-rotors or quadcopters, but it's a nice piece of tech to have because it allows us to bring in our battery voltage, and it does a few things for us. It converts it down to 5 volts as well as 12 volt regulated or just unregulated input power, and allows us to take that power out to our ESCs, to all of our motors. It also allows us to do custom things like send 5 volts out to the camera or send 12 volts out to some other components. And again, we'll talk about the specifics of all those and how many different PDBs are out there on the market. In some builds, you might use an electronic speed controller that has what's called a battery eliminator circuit, in which case you can hook battery power directly up to the number 1 ESC, and then from there you can actually wire it up so that you don't need a power distribution board. In our case, we're using a power distribution board specifically because we have a camera, a transmitter, and some other components, but again, it's not necessarily needed on all quadcopters. A controller and a receiver is a necessity in our case because we're having a quadcopter that's completely flown by a controller on the ground. There are cases where you can design one to fly by itself based on GPS coordinates and waypoints, but in our case, we have a remotely piloted vehicle. So that means we're going to have a controller, a person on the ground that's controlling it directly, and a receiver on our quadcopter. The next thing in our specific case is a camera, TX, and tilt motor. Now the TX part of the camera is a transmitter. So it's going to take our camera signal and it's going to send it down to us so we can view it on a monitor. The tilt motor can be a servo or a brushless gimbal motor, but in general we're going to be using a tilt motor so that we can take the camera and tilt it up or down based on what we want to look at. So these are the basic components or basic parts of most multi-rotors. Now this does also fall in line with various other types of vehicles. A lot of this can apply directly to ground vehicles as well. So if you're using this course and you're trying to plan out a build, whether it's a quadcopter or an airplane or some other vehicle like a car or an RC truck, a lot of this is going to directly translate to those as well. The flight controller that we use can be used on airplanes, it can be used on ground vehicles or boats or motorcycles as well. So it all will directly apply to all of those categories. So now the last thing I want to talk about in this lesson is the big picture. And understanding the big picture helps us understand what these components do and how it helps us plan them out. So the overall weight of any flying vehicle is extremely important. You can't make a very heavy flying vehicle and have it fly for a long time and be maneuverable, all the different things that we need in our design criteria. So as we look at the overall weight, the batteries that I've planned to talk about in this course are between 100 and 300 grams each. Now we'll get into picking the components later and what it all means, but right now all you need to know is that we're going to be using 2 batteries, so we're looking at generally 200 to 600 grams total weight on our vehicle. The components that we're using, which includes the motors, the props, the speed controllers, the power distribution board, the flight controller, the receiver, all the other stuff that's not the batteries, that's going to be between 200 and 300 grams. The reason I gave a range there is because we can mix and match parts, we can change things out and have a big effect on that weight. Now we're going to be shooting for the 300 gram range, but again, there's a range there because you can use different cameras. You can remove the tilt servo and have a fixed camera. We can maybe change out our power distribution board. Different things like this can have an effect on them. And lastly, we have the body, which I have to be determined. Now, in general, when you're planning out a quadcopter, it's a good rule of thumb to have your battery weight be between 50 and 65% of the overall vehicle weight. Now, there's no hard and fast rule that it has to be that, but in general, when you get your batteries over about 65% of the overall vehicle weight, you're really just adding more weight to spin the motors to carry the weight of the batteries. So there's a fine line between that 50 and 65% where you're not really adding anything additional to the flight of the vehicle, in this case our quadcopter. So if we look at this, and again remember we're using 2 batteries, we're looking at 600 grams of batteries, 300 grams of components. So to keep with that roughly 50% rule, we're going to be looking at roughly 300 grams for the body. So that's going to be our starting point and our target for the design body. Of course, if we can make it lighter, that's better because we can add more components and still have the same thrust ratio. The next thing that we want to talk about in the big picture is the thrust, because this is actually the force that gets us off the ground. Now the thrust comes down to 3 main factors: the propeller size, the battery configuration, and the motor we choose. Now the reason all these are important is because all 3 of them go together. Now certain motors are specifically designed for certain propeller sizes. The motor that we're going to be using is generally used on 5 or 6-inch propellers, but it's only used on 6-inch propellers in certain battery configurations and 5 in other battery configurations. This information comes directly from the motor manufacturer, and you can also test it by building a test rig with a scale and a restrained motor. But for right now, we're going to be using the information that comes directly from the manufacturer and comparing how changes in the battery and the prop size will affect the thrust that we get. Because remember, we're planning for 600 grams of battery, 300 component, and roughly a 300 gram body. So that value, that 1200 grams, is what we're looking at for the amount of thrust that we need. And we're going to plan all that out, and we're going to talk about those in general and specifically in other videos. In this design criteria lesson, we're going to carry on with part 2 of our component selection. After completing this lesson, you'll be able to understand multi-rotor component basics, apply basic calculations to compare components, and make informed design decisions. So we want to carry on with the big picture of all the components that go into a quadcopter. Now first we want to talk about what some of the numbers of these components mean. You have to understand what these numbers mean in order to help you pick them yourself. Now if you just want to follow along using the exact components that we've picked out for this course, that's completely fine. But if you're taking this course to help you understand not only the design aspect in Fusion 360, but also more about quadcopters in general, I want to make sure that we pass along that knowledge so that you're armed with everything you need to design your own. The motors that I've picked for this course are made by a company called DYS. The specific motor is an MR 2205-2750 kV. Now the important thing here is we need to figure out what those numbers mean. Right now those numbers are meaningless. If you've never built a flying quadcopter or multi-rotor before, you've never messed with any RC components before, this means absolutely nothing to you, and that's completely fine. But we want to break it down so that you understand what these numbers are and how they will affect the performance of your device. So now the MR. The MR is actually just the code that DYS uses to signify that this is one of their racing motors. The next four numbers, the 2205, are going to be very important to us. The 22 is the diameter and the 05 is the height. Now these aren't the outside dimensions of the motor, but rather the diameter and the height of the stator. These are going to affect the performance of the motor. Now in general, this size motor is great for a 250 series quad. That means 250 millimeters between opposing motors on the X pattern of the quad. So this is a great motor choice or a great size choice for the size of quad that we're building. We're going to be in roughly the 250 to 270 millimeter range for our size, so this is great for what we're doing. But the 22 and 05 numbers will determine things like how much torque the motor has, how high of an RPM it can go to, and so on. Now the 2750 kV is a very important number. Now the kV in the case of these brushless motors stands for constant velocity. Has nothing to do with kilovolts or anything like that, which you would assume if you have any experience in electronics, but the kV generally stands for constant velocity and lets us know what the RPM is per 1 volt. Now this is important because the voltage changes based on our battery configurations, and we'll talk about batteries in just a second. But in general, we're going to have two main battery voltages that we're going to be dealing with, 11.1 and 14.8. Now, this kV number, or this constant velocity number, is multiplied by those voltages to give us the max RPM unloaded with no prop on it. So if we take 11.1 and we multiply it by 2750, we get roughly 30,500 RPM. If instead we take that 14.8 and multiply it out, we get almost 41,000 RPM. So why is this important to us? Well, as we look at the specs for this motor, without having to go through any spec sheets or look at anything else, just looking at the part number, we're going to know the diameter and the height of the stator, and we're going to know roughly what the max RPM is going to be. Now, as you look at motors, the higher the kV number, the higher the RPM, generally they're set up for smaller props. If you have a lower kV number, let's say that it's 800 kV, those are generally set up for larger props, which will spin slower, but still give you a lot of thrust. So as you pick through catalogs and you're looking for motors that you want to explore and think about more, you can look at these kV numbers and you can look at the 2205 and know that you're in the right ballpark. Now for the MR2205 series, DYS actually does offer a couple different kV values. I think they have a 2300, which is a little bit lower than this, which means that we're probably spinning 25 to 30,000 RPM in the various voltage ranges. So that means it's probably going to be a little bit more torquey motor and have less top speed or less higher RPM. The next thing that we want to talk about with the motor is thrust. Now this is going to come from a chart that we're going to talk about in another lesson when we get into the specifics of picking out what these mean. But the thrust is based on the battery, which in our case is going to be the voltage, and it's also going to be based on the prop. Now any reputable motor manufacturer is going to give you this information. They're going to give you a chart, they're going to give you a list, and they're going to tell you what props this motor was designed for. In our case, DYS tells us that a 5 by 4.5, which is 5-inch diameter by 4.5 pitch, and a 6 by 4.5 are going to be the ideal prop choices for this motor. Now they give you the thrust outputs at various percentages for 11.1 volts on both the 5 and the 6-inch prop, and then they give you the outputs for the 14.5 volt setup on a 5-inch prop. So this is going to be great information. It helps us pick out what batteries we want to use, how much amperage we need for the flight time we want, and how much thrust we're going to get out of it. The next thing to consider when you're looking at motors is the amperage draw. And again, this is going to come from that that list, that value that we're going to talk about in terms of the thrust and the input and the output. But generally, the amperage draw, or how much the motors are going to use, increases with throttle. Just like it does in your car, when you press the gas pedal down, you use more gas. Pretty simple to think about it in that relationship. But in our case, we're going to have an ideal range where we have a certain RPM or a certain percentage of throttle that's going to give us the most out for the least amount in. So we're going to look at this and we're going to try to plan for the maximum amount of thrust that we need for just a stable hover with the minimum amount of input. So we're going to look for the 25 to 35% input range, and we're going to try to plan out our output or the thrust that we need for that range. And lastly, when we talk about motors, we're going to talk about an ideal prop setup. Now again, it's going to be based on battery, it's going to be based on the weight and the amount of thrust we need, and we'll get into the specifics of those. So next we want to talk about battery specifications. The batteries that I picked out for this course, I have 3 different battery choices that we're going to look at. They're all Turnigy, they're all LiPo, and we want to explore what these numbers mean. Now the battery that we're talking about here is a Turnigy LiPo 3S 1500 mAh 20 to 30C. Now the first thing that we want to understand is the LiPo part of it. This is a lithium polymer battery, and this has a very high discharge rate while being fairly light. And these are standard in the quadcopter and flying device, flying airplanes and helicopters and all these things. It's a common type of battery. Now it's one that we need to be very careful with when you're charging it and discharging it and so on. So it's important that we understand what these numbers mean. So first let's talk about the 3S number. Now the 3S stands for 3 cells. Each cell is going to be roughly 3.7 volts. So when we talk about a 3S battery, that's an 11.1 volt battery. When we talk about a 4S battery, that's going to give us 14.8. Now when we were just talking about the motors, remember that 11.1 volts or 14.8 volts will change the max RPM of the motor. Now at 11.1 we were roughly 30,500 RPM, but we went up to about 41,000 RPM when we went to a 4S or a 14.8 volt setup. The next number is the 1500 mAh or milliamp hour. So when we talk about amp hour or milliamp hour, we're talking about how much current a battery can supply for 1 hour. Now in our case we're going to be using 2 batteries. They're going to be wired in parallel, and that's going to give us the same 11.1 volt or 14.8 volt, but it's going to give us twice the milliamp hour, twice the capacity. The last numbers, the 20 to 30C, is the discharge. Now this number, again, it's a very general term and it really helps you when you're comparing batteries, but you never want to plan out a build where that 20C is exactly what you want. You always want a little bit of a margin in there. So the discharge is you take the 20C, the 20, and you multiply it by the 1.5 amps. So what this tells us is that our 1500 milliamp or 1.5 amp battery can supply 30 amps continuously until you run down to the point where you want to stop. So this number is telling us that this battery can handle that amount of supply without overheating or without damaging itself. That's the low value. That's the 20C number. The 30C is essentially a burst. This is telling us that 30 times 1.5 amps will allow us to draw 45 amps for roughly 5 to 10 seconds. Now, this is important if you're planning out a fast drone, a racing drone, where you're going to be trying to get as much out of it for a very short period. Now we're not going to be pushing these batteries to any extent like that, but that's what these numbers mean, 20 to 30C. So let's talk a bit more about multi-rotor basics. We know what components we need. We know the sort of general idea of what is going to have to be on our quadcopter, but now let's talk more specifics. When you're standing on the ground, when you're flying a quadcopter, when you're controlling the throttle or the pitch or the roll, you're going to be sending a signal to an RX or a receiver module. Now again, this is paired directly with our controller. In most cases, you can buy the controller and the receiver as a pre-paired set. In some cases, you'll have a controller already and you'll simply pair it to a new receiver. So the first picture shows the receiver. The gray wire is the antenna wire, essentially where the signal's coming in from. And then each of the wires going out, the yellow, the green, the white, the blue, is an individual signal. One of them will be throttle, one of them will be for roll, one of them will be for pitch, and those will go directly to the flight controller. And this is the brains of the quadcopter. Now the flight controller has several sensors on it, a gyroscope, an accelerometer, and additional inputs that you can plug into it for various things like GPS. And it knows exactly which direction's forward. It knows if it's pitching or rolling or yawing, and it also knows what the current speed of all the motors are. Now the flight controller is configured by you, and we'll go over that in our course as well, and it'll do things like it'll know how quickly you want your quadcopter to react to your inputs. It'll know what type of flight you want to do, if you're doing acrobatics or if you're just trying to achieve slower, more stable flight. That can all be programmed into these flight controllers. So the signal sent from your controller to the receiver to the flight controller board, and then that converts whatever we do to a motor output. It sends that signal to the ESC, or the speed controller, and then the speed controller relays that on to the motor. And those are the very basics of what we need to control the quadcopter. Now we can get into various add-ons, additional things that we can put on our design to increase its functionality, maybe make it easier to fly or safer to fly. And the first of those is a PDB, or power distribution board. Now the one that we have on the screen here is fairly unique because it also includes some additional functionality by using an OSD, or an on-screen display. But this will allow us to take in the battery. It'll take the battery voltage. It'll send directly out to the ESCs. It's powering the ESCs, and they're waiting for a signal from the flight controller to then relay that onto the motors. So it takes that voltage and sends it out, but it also converts the voltage down to 5 volts so that we can power our camera, we can control our servo, and we can have a 12 volt or direct battery voltage, send that out to the transmitter for the video signal. So the OSD is on-screen display, and this specific board allows us to take the video signal in, and then when it sends it down to us on our monitor at the ground, it'll display the battery voltage for us. Next we have the camera, and this specific camera that we're going to be using comes with a tilt servo and a pan servo on it. Now I'm modifying this one for our design to only have tilt, but this is a great option because it has a self-contained unit with the camera as well as the 2 servos, so it's very easy to incorporate into a generic build. Next we have the transmitter that sends the video signal back down to us on the ground. Various different options when you're picking out these. You have different antenna options, you have different input voltage options, different signal options, various things that we can play with and configure between the camera and the transmitter module. And again, we'll get into all that when we pick out our components, but for right now just understand what each of these is. Then we also have some additional things that we can add into our build to do various tasks. So servos or brushless gimbal motors, these are things that we can add on to do various tasks for us. For instance, a servo could be used to open or close a claw to allow us to pick things up or drop things off. Now in our case, we're planning for a fairly small quadcopter. We're not going to have a lot of lifting capacity, but these are things that we can use these types of devices for. We can also add additional sensors or cameras, things like GPS or ultrasonic sensors that will allow us to control the quadcopter, and if it senses things like walls or any obstructions, it can intervene and stop us from flying into them. In this design criteria lesson, we're going to carry on with part 3 of our component selection. After completing this lesson, you'll be able to apply calculations to select components and make informed design decisions. In this lesson, we're going to be focusing on the amount of thrust provided by our motor and how our battery choices are going to affect both the lift as well as the flight time. So the DYS motor that we're talking about here is the MR2205-2750 kV. We already know that the 22 is the diameter of the stator, the 05 is the height of the stator, and the 2750 or constant velocity is multiplied by the voltage to give us the max RPM unloaded. But what does all this mean? Well, DYS provides these thrust charts with their motors so we can reference the motor, how our battery choices are going to affect things like the thrust, as well as which propellers that we want to choose. The first thing that we need to consider is the mass. Now, I've picked out a couple different batteries that we're going to talk about. The smallest 3-cell battery that we're going to talk about gives us roughly a total mass of 814 grams. The largest 4-cell that we're going to talk about gives us a total mass of roughly 1130 grams. So at this stage, we're not too concerned with the amperage or the amount of current that the battery can push out. We're solely going to focus on the 3-cell and 4-cell differences and how they apply to the thrust. So first, let's take a look at the example at 50% input with a 5x4.5 prop on a 3-cell system. So the 3-cell or 11.1 volt system will provide 371 grams of force. Now this is times 4 because we have a quadcopter and 4 motors, so the total is going to be 1484. We need 814 grams bare minimum to be able to get off the ground, and we have 1484. This is not quite the 2-to-1 ratio that I'm looking for, but it is enough for us to get up in the air and fly. Now when we talk about our thrust ratio, or the amount of force that we provide as opposed to the amount of weight that we need to lift, I like to shoot for a 2-to-1 at 50% throttle in this design case. This is going to give us plenty to fly and enough room that if we go up to 100% throttle, we're going to have great maneuverability and we can get somewhere fast. But let's take a look at some other numbers. For the same prop on the same motor, but a 4-cell system or 14.8 volts, we now have 561 grams of force. Multiply that by 4, we get 2244, or 2,244. Now we have to lift 1,130. We're pretty close to that 2-to-1 ratio. We're at about 1.95, so this is pretty good. The input at 14.8 volts is giving us a lot more output. Even though we have to lift more mass, we can still account for it and get a better thrust ratio. But now let's take a look at what it means to do a 3-cell system with a 6-inch prop as opposed to a 5. So at 50%, we're now getting 481 grams of force. So this is 1924 once we multiply it all out, and we're still only lifting 814 grams. So this gives us the best thrust ratio. But we have to be careful when we talk about this because instead of needing 8 amps of current at 50% on the 5-inch prop, we now need 12 amps of current. So if we factor in the amount of current needed for both of these setups, at 11.1 volts, 50% on a 5-inch prop, we need 8 amps. However, at 11.1 volts on a 6-inch prop, we need 12 amps. So we're actually drawing quite a bit more current. So even though we're lifting more and we're not really increasing the mass, we're not going to have nearly the same amount of flight time. So let's take into account the rest of the equation. We now want to look at the battery and how that's going to affect things. So we want to take a look at the difference in mass, we want to take a look at the difference in the voltage and the current. So the 3 batteries that we're talking about here are all Turnigy. The first one is two 1500 milliamps wired together. The second one is two 2200 milliamps wired together, and the third one is a 4-cell system with 2650 milliamp hours wired together. By wiring 2 batteries together, we're able to double the current but keep the same voltage. So this is a nice way for us to increase our capacity, increase our flight time, and be able to add a bit more mass to the system to get that roughly 50 to 66% mass being part of our batteries. So as we look at this, our smaller 3-cell system is 214 grams for 2 batteries. Our larger 4-cell system is 530 grams. And right in the middle, we have 4.4 amp hours in a 3-cell system at 376 grams. Now remember, all 3-cell systems are going to be about 11.1 volts. The 4-cell system, however, is 14.8. So as we look at these 3 cases, we want to take a close look at not only the difference in the mass, but how the voltage is going to change the overall equation. So the next column that we're looking at is going to be the 5x4.5, or the size of our prop. I omitted the 6x4.5 prop because we're really planning for a 5-inch prop here, and the reason we're doing that is because we want to be able to configure the battery. Now there was no 6 by 4.5 prop shown on a 14.8 volt setup. Now that's because the 14.8 volt is not going to be spinning that 6-inch prop. Ideally, DOIS wants you to run a 5-inch prop on that system. Because the 5-inch prop was available for both the 3-cell and the 4-cell, I want to make sure I stick to something that allows me the flexibility to run the 4-cell batteries or run the 3-cell batteries. So now you're wondering, where did these numbers come from? 14 amps, 20 amps, and 18.5. Well, if we reference the thrust chart, we can take a look at each of these numbers. First, we have to lift 800 grams. So if we divide that by 4, each motor needs to be at least 200 grams of force. Now I do want to note that we're taking the bare minimum total mass and we're using that as our thrust. We're going to need more thrust for us to actually get off the ground and fly, but this is a great way for us to baseline everything and take a look at the raw numbers. So in order for each motor to be able to lift 200 grams, on a 5 by 4.5 prop on a 3-cell 11.1 volt system, we fall between the 25 and 50% input. We're pretty close to 25% because that gives us 175 grams, while the 5 by 4.5 prop on a 50% setup gives us 371. So I estimated this at about 3.5 amp input to give us 14 amps when we multiply it by all 4 motors. Now as we look at this, our battery is only providing 12 amps, and you might be wondering how I arrived at that number. Well, remember the amp hour value is how much amperage it's going to supply for 1 hour. With our battery, if we take 3 amps for 1 hour, we can provide roughly 6 amps for half an hour or 12 amps for 15 minutes. And again, to simplify all the numbers, I'm taking 15 minutes of what these batteries can supply, and I'm taking a look at how that compares to the amperage input we need just for the bare minimum. Now remember when we talked about our design criteria, I wanted at least 15 minutes of flight time. So the 15 minutes supply on the battery will help us understand how that's going to work. If we take a look at the larger capacity 3-cell system, instead of 3 amps, we now have 4.4 amps. But we have to lift 975 grams. If we divide that by 4, we have to have 244 grams of lift for each motor. Now again, that falls between the 25 and 50%, but it's quite a bit farther away from the 25%. So I estimated about 5 amps or 20 amps for all 4 motors. Now the larger capacity battery of course gives us more amperage, but it only supplies 17.6 amps for 15 minutes. We need 20 amps, we're only getting 17.6. We're still not quite there for 15 minutes of flight time. Now if we take a look at the 4-cell system, we have to lift quite a bit more. Each motor has to be able to provide 282 grams of force. Now on a 4-cell system, we're now at 14.8 volts, the same prop, and we're right about 25% input. Now this is great because we have 280 grams for each motor, and we're only pulling 4.66 amps of current. If we take a look at this, the battery is going to provide 21.2 amps because it's got larger amperage. So 21.2 amps for 15 minutes, we only need 18.5 to fly. This is going to give us enough amperage to be able to fly for 15 minutes. Now, the way that we can address this entire problem is we can take a look at the total mass, we can take a look at the battery setup, and how that's going to affect our flight time. With less mass, we need less amperage to fly for the same amount of time. Because we're talking about the amount of thrust we need and how much throttle input that's going to be, the 4-cell system looks like it's going to give us the best bang for the buck. It can be run at 25%, it can give us enough thrust to get off the ground, and we still have 50, 75, and 100% throttle to get quite a good thrust ratio out of this. At 280 grams, that is a 1-to-1 thrust ratio at 25% throttle. When we go to 50, we have 561 per motor, 75, we've got 908, and as we go down the list at 100% throttle, each motor is providing 965 grams of thrust. Now that means that one motor can almost provide enough thrust to get off the ground. This is giving us a roughly 4-to-1 thrust ratio. This is going to let us be really maneuverable in the air, get to where we need to fast, then we can reduce the amount of throttle and hover and just keep the throttle at the lower roughly 25% and survey certain areas. So overall, when you start to design something like this, whether it's a quadcopter or anything, you want to take a look at this type of data, you want to compare your options, and you want to figure out what the best route's going to be. Now I've actually built this setup on a 3 amp hour system on a 3-cell battery. And I can tell you that from my experience, I was able to fly for about 8 to 10 minutes on this setup. Some maneuvers, but mostly hovering. So these calculations for 15-minute supply at 12 amps, requiring about 14 amps, it's pretty realistic. It gives us a good idea of where we need to be. So this tells me that if we decide to go with a 4-cell system with the larger capacity batteries, we're going to be able to fly for probably about 20 minutes on that setup. So at this point, we've given you a lot of information on how to pick components to design a quadcopter. Now, as we move forward, we're going to be starting our build by using the DYS motors we talked about. We're going to start with the smaller capacity batteries, the 3 amp hour 2 battery setup, which is the lightest setup that we have. And we're going to take a look at how that translates to our real world flight time. Being able to keep the same propellers, to keep the same motors, and simply upgrade the batteries to larger capacity 4-cell systems is going to give us quite a bit more flight time. So we know that we have that option to increase the batteries as long as we design it so that the batteries are centered on our components and we center all the mass on those batteries. Now again, we're looking at roughly 50 to 66% of our mass coming directly from the batteries, so they will have the greatest effect on the balance of our components. As we move forward in our course, it's important to remember all these values, remember where they came from and how they apply to what we're doing. Even though the course is laid out so we use all the same components that we're talking about, it's perfectly acceptable for you to take a look at these and figuring out better components to use, whether it's a different motor, whether you're planning for a different battery system, or simply sourcing different components so that they're lighter or easier to manufacture or put into our design. I will give out a full parts list, and with this course I've also supplied an Excel spreadsheet that has all of this information on it as well. So you can take a look at that, the components that we're using, and how that correlates to what we're doing here in this course. For this design criteria lesson, we're going to carry on with part 4 of our component selection. After completing this lesson, you'll be able to compare video components and options and make informed design decisions. First, let's talk about the camera system parts that are spec'd out for this series. For the camera, we're using a Fat Shark 700 TVL CMOS camera. It's capable of NTSC and PAL. For video transmission from the quadcopter down to the ground, we're using a SkyZone TS5823. For the monitor and receiver, we have a 7-inch 1024 by 600 monitor that's made by FieldView. So first, let's talk about the camera. So the Fat Shark 700 TVL CMOS camera, this is a good system because it has a few things going for it. The CMOS type camera is lightweight, it has low power consumption, and because of the technology is fairly inexpensive. The specific unit has a few extra things going for it. It has removable lenses so we can change the field of view, and it also comes with a pan and tilt servo already built into it. Now in our case, we only need tilt, so I've deconstructed it a bit. I've taken off the pan servo and we've modified it slightly so that the servo is going to be held directly with our 3D print. When we're looking at cameras, there are a few things that we need to be concerned with. First of which is the type of camera. Now there is a CMOS and there's a CCD camera. Generally the CMOS cameras are going to be less expensive because of the technology, but they're also going to be lighter and have lower power consumption. While a CCD type camera, or really the chip that's on the camera, is going to be more stable, less receptive to interference in the lines, but because of this it's actually going to be heavier, it's going to use more power. Because we're completely concerned with power consumption and weight rather than the quality of the video, this is why we went with a CMOS camera. The 700 TVL is actually the number of lines on the image. The 700 TVL is actually a fairly high number, so we get a really good, high quality color image out of this camera. For output, NTSC or PAL is selectable on this specific camera, so we can decide how we want to transmit the video. For video transmission, we need to take the camera signal and we need to send it back down to the ground. To do that, we're using a SkyZone TS5823. This is operating at 5.8 gigahertz and has 32 channels. This also allows us to send both audio and video. Now this has a few things going for it. First of all, it's small and it's lightweight. This is again important because it's our main focus to keep the overall system as light as possible to increase flight time. This specific unit, running at 5.8 gigahertz, will give us about a mile of range with no obstructions. So if we're flying in an open field or an open area where we don't have a lot of tree coverage or buildings, we can get a pretty good range to get our video signal back to us 1 mile away. This specific unit has a set of dip switches on the board that allow us to change the channel. So we're operating at 5.8 gigahertz, but we have up to 32 different channels that we can operate on. And this specific unit also comes with a cable that allows us to run it directly to a GoPro. So again, this goes back to being able to configure our system. If we want to run a GoPro camera, we can plug the micro USB that comes directly with this board and transmit both audio and video back down to the ground fairly easily. The nice thing about running a GoPro is it's got a self-contained SD card to store the video, and it also has an onboard battery. So we don't have to wire the GoPro up to the system, with the exception of sending the video back down to the ground with a live feed. And lastly, we have the monitor and receiver. Now the one we're using is a FieldView 777. And this is a great option because it already has a 5.8 gigahertz receiver with 32 channels on it. It's a 7-inch 1024 by 600 color monitor, and it also has audio capabilities. It has video in and video out, so we are able to send the video out of this monitor and record it on another device if needed. The specific one is fairly high resolution. It matches the 32 channels that we have on our transmitter. It's 2.4 gigahertz protected. And that means that the 2.4 gigahertz frequency we're operating at with our controller that sends the signals to the quadcopter that tells it to go up or down, pitch left or right. It's not going to affect the video quality at all because this specific one is isolated from the 2.4 gigahertz frequency. This monitor also has a built-in battery, and with a charge it can last up to 2 hours. And again, it does have audio capabilities as well as a headphone jack on the side. There are many different options that you have when you're trying to view the video on screen. Because we're building a similar type of quadcopter to an FPV, or a first-person view quadcopter, there are plenty of on-the-shelf different types of goggle systems where you can get the 5.8 gigahertz signal directly to a set of goggles that you wear, so that way you can see exactly what you see from the quadcopter when flying. Now the reason I chose to go with a monitor rather than a goggle setup is because the monitor can be viewed by somebody else fairly easily because it is a 7-inch monitor. It also allows us to fly line of sight with the pilot while somebody else is viewing the camera. So if you just have a set of goggles and a first-person view setup, then you're not going to be able to have anybody else look at the monitor or send the video signal out to another set of monitors to have more eyes looking at what we see on the ground. So again, this is a great option, fully self-contained unit, and if you search around online you can find various prices for these that range from about $100 to $150. So overall, the camera system parts, let's talk about what we have. We have a lightweight camera and a transmission module. The SkyView TX module operates at 5.8 gigahertz and has 32 channels available. We have a high resolution, the 700 TVL color output camera. We can also swap out a GoPro camera and we can transmit audio and video easily with the TX module that we chose. We're using options that have low power consumption. Because our camera is a CMOS chipset, it actually operates with lower power consumption than a higher quality CCD camera. Our camera is currently running at about 5 volts, while the transmission module is running between 7 to 24 volts. So there's a wide range of voltage that we can operate on, but we need to provide at least 7 volts to be able to transmit the video down. The good news is that the battery setup we're using is 11.1 volts or 14.8 volts. We're using a power distribution board, so we can automatically supply the voltage needed to both things. We also have camera tilt included with the camera that we chose. There are plenty of camera options on the market. Some automatically have the transmission modules built onto them, including antennas. So if you're looking to build your own system, don't think that you have to go with the cameras that we chose. If you want to use a fixed camera, or if you want to build your own tilt setup, you can buy individual servos, you can buy specific cameras and transmitters, and you can pick and choose which components you want. You can very easily get away with using a GoPro that you have because we're planning our build so that we have enough capacity to lift a GoPro or additional equipment as needed. So that might be a great way to get a first-person view by using a fixed GoPro without including the tilt module. Plug it directly into the transmission. So now let's talk a little bit about how we can get the camera to tilt. There are two different pieces of equipment that we can choose. One is a brushless gimbal motor, and this is very similar to what our propeller motors are going to be, and the other is a servo. Now each of these have pros and cons, and I just want to pinpoint a few things here. The gimbal motors are heavy, and generally they're only seen on higher capacity quadcopters or multi-rotors. They do offer smooth motion. Because they are brushless, they don't have notches or different areas where we're dealing with a gear reduction system and a stepper motor. They do unfortunately require additional parts. Generally, when you deal with a brushless gimbal motor or multiple gimbal motors, you will have its own controller. Now the own controller will also have a similar type of ESC that we see when we're driving the motors that have our propellers and provide our lift. So keep in mind that if you decide to go with a gimbal setup on one or two axes, you're going to be adding probably an additional 200 grams in just the gimbal motors alone, plus you will need an extra circuit board that can help control that. However, with the servo motor, we generally have a fairly light package. We will get jerky motion because we do have a gear reduction inside of the servo, but it does plug directly into the CC3D. Now I do want to make an important note here. Gimbal motors are generally used for stabilization. Now you often see these on 2 or 3 axis rigs when somebody's running a high quality camera, whether it's a video or still camera, to make sure that they isolate the motion of the quadcopter and keep the camera stable. Now this is great if you're doing high quality photography or you really need that stable camera image. In our case, the weight is going to be more important than the jerky motion of the camera tilting. We are going to be using manual control of the servo, so we don't really need to worry about that smooth motion because we're going to be turning a dial on the controller to look down or up as needed with our camera. We can use automatic stabilization with our CC3D flight controller to control a servo to automatically tilt the camera up and down based on the angle that the quadcopter is flying at. So while we will get a little bit of jerky motion, we can achieve the same type of thing that a typical gimbal setup will require. However, we can do this without having additional equipment because we can send a 5-volt signal directly to the servo to control it without having any additional boards, IMUs, which are inertial measurement units, or any ESCs. In this design criteria lesson, we're going to talk about component location. After completing this lesson, you'll be able to understand multi-rotor mass location and make informed design decisions. First, we need to talk about the mass of each component. Now currently we have 4 motors, each of which is 28 grams. There will also be some mass associated with the propellers, but this is negligible, and since it's spinning, there's a little bit more advanced dynamics that we need to talk about. But for right now, let's just use 28 grams per motor, and we have 4 of them. The flight controller, which needs to be centered on the quadcopter for the best performance, is 7 grams. Now I chose the Micro CC3D because it's fairly small size and has all the functionality we currently need. If we tend to upgrade the flight controller, that mass could go up, but it's always going to be centered, so it doesn't really affect the overall performance by shifting mass around. The batteries are going to be a large portion of the mass. we generally want to shoot for between 50 and 66% of the overall mass. Now this includes the body, all the components, and that's where we want the mass of the batteries to fall. Because we talked about several different ones, from smaller capacity 3 cells to a larger capacity 4 cell battery, we have a range here of about 100 to 265 grams each. We're going to be looking at and planning our overall design for the larger batteries, but we can also use the smaller ones as well. So we're looking at 2 batteries at 265 grams each. The ESCs, or electronic speed controllers, are currently 20 grams. Now these aren't the lightest ones, but we're using these because they're set for 40 amps of current and they have a 500 hertz response. So this means that the resolution on the response is very fine. Now the reason that we're using these is because we want to be able to switch back and forth between 3-cell battery setup and a 4-cell. When we're on a 3-cell setup, we're only drawing about 27 amps max, so the 40 amp is a bit overkill for that scenario. But if we decide to use a 4-cell battery setup, we're going to be pulling closer to 36 or 37 amps. And in that case, we'll actually need the 40 amp. So that's why we're using these, and we're sacrificing a little bit of the weight by having the ability to change our battery configuration. The controller RX module that receives the commands from the ground is about 13 grams. It's actually a little bit lighter than that, but I'm using a higher rate just in case we decide to change that module. I want to make sure that the location of that mass makes sense. The PDB, or power distribution board, has a fairly large range, from 7 to 22 grams for some of the boards that I've played with. Now the smaller end, the 7-gram board, is the one we're going to use in the final build. The 22-gram board has less functionality, but it's much easier to use because it includes bullet connectors that can be easily plugged into and out of when you're testing your setup. So sometimes it makes sense to use a heavier component while you're in the testing phase and downgrade to a smaller component with completely soldered joints for the final build. Our camera and servo are about 30 grams. The overall package of the camera that was purchased was 44 grams, but we removed one of the servos, so that way we dropped some of the mass. And lastly, the video transmit module that sends the video signal back down to the ground is 10 grams. Now one thing I did exclude from this list is the body. Of course the body is going to be designed, and we're shooting for about 300 grams. Now let's talk a bit about the mass location. When we're designing a quadcopter, the plane at which all the propellers are spinning is considered the thrust plane. Now the direction or the location of the center of gravity in relation to that thrust plane changes how it behaves in the air. If we have the mass and the center of gravity located in that thrust plane, so it's the center line of the thrust plane, we have a very quick direction change. This means that without the mass above or below, it's very easy for it to change directions and roll about the center of its axis. So ideally, if you want a very responsive quadcopter, you're going to work toward putting that mass directly in the center of the thrust plane. If it's below the thrust plane, you get increased stability, but you reduce the agility. Now if you notice a lot of the off-the-shelf quadcopters that have camera gimbals on the bottom of them, or the larger ones that are used for filming and taking pictures, these will have a setup where the propellers are all on the top and all the mass is below the thrust plane. Now this means that it's very stable to fly, but it is very sluggish and slow to change directions. Now generally when you have a camera type quadcopter that you're taking aerial photography for, the agility is not really that important. But in our case, we're designing for something that is fast, can accelerate, and get to locations quickly so that we can search. Now if you put the mass above the thrust plane, this is an interesting scenario, and it has the tendency to flip. Now if you look at a lot of FPV or first-person view racing quads, a lot of times you can see that batteries might be placed on top of the chassis or below, and it has differing effects on how the quadcopter maneuvers. If you have it on top, it makes it a little bit easier to flip over, but harder to stop the flip. If you have it below, it's harder to initiate a flip, but it's much more overstable to help stop the flip. So these are all things that we need to consider when we talk about placing mass on our quadcopter. Now if you're buying an off-the-shelf chassis, they're fairly configurable. There's lots of slots and holes where you can zip tie or affix different components, so you can play around and move mass around and see how things behave. So let's talk about the mass location with some screenshots of the final design. So what we have here are the location of the battery, which is roughly centered on the thrust plane. Now you'll notice that the batteries are just a little bit below the thrust plane, and that's because we have components above them. We have the power distribution board, the camera and the transmit module, as well as the ESC servos. We also have the motors. In this orientation, we have the motors flipped and the propellers below them. Now, in most cases, you'll have the motors pointing up and the propellers above. Now, the reason that we're doing this is for airflow and protection, but we'll talk about that in just a second. So the batteries together are about 530 grams. So this is by far the heaviest group of components. So having it just slightly below the thrust plane allows us to offset the rest of the mass. Now we could move these up or down, but in this instance we have them kicked up just a little bit so that we have more protection during a crash or when landing. The motors, in this case, we only see 2 of them. But if we look through it, because we have 2 on each side, we're talking about roughly 56 grams. We have 4 ESCs, or electronic speed controllers. Now in this case, we have 40 grams on each side. Now if you'll notice, everything is working off of symmetry. We're trying to keep everything as balanced as possible, both left to right, fore and aft, and up and down. Now the ESC's locations are on the top side of the chassis right now, but they actually can be affixed to the top or the bottom, depending on how we want to move the mass around. Now if we look at this from the top, let's take a look at the motor locations. Again, everything is working off of symmetry. The center line of the vehicle in both directions, we have the motors symmetric front to back and left to right. Now, this is important, again, for balance. We want to make sure that everything is balanced and we keep the mass as close to the center point as possible to make it very agile. Now if we take a look at the ESCs, each of them are 20 grams and they're located in this area. Even though we can't see them, they are located underneath that section of the wing. The camera and the tilt servo are located at the front. Now the reason it's located here is for good visibility. We want to make sure that we're not looking at the propellers, we're not obstructing the view, but we want to make sure that we're still protected. So the camera is below the top and it's well above the bottom, so they're not really worried about any collisions or obstructions. And we also have the extensions around the propellers to protect this if we were to bump into a wall or something. Now on the back side, we have the video transmit module. This is also fairly close to the location of the controller receiver. Now the controller receiver is placed a little bit closer to center, but again, these can move around. Now right in the center, we have the CC3D, which is the flight controller, which is 7 grams. And again, it's best to place that at the center of rotation on the vehicle. So if you draw a cross from each of the motors, right in the center, that's exactly where you want to place the CC3D. It also is directional. It needs to know which direction is forward, and that way it can control the motors. And the power distribution board is located below this. Essentially, the batteries, the power distribution board, and the flight controller are all sandwiched right in the center. Now the power distribution board is sandwiched in the center because it makes sense for symmetry in terms of wiring for the ESCs and getting power out to the motors. Lastly, let's talk about the batteries. Now from this top view we can't see the batteries, but they're located center, and again they're located just below the thrust plane. Because they are the greatest mass, we want to make sure that they're located at the center, both when drawing a cross between all the motors, and that we get them close to the thrust plane so we have a very agile craft. Now let's talk about airflow restriction, because this is also important. We're able to place the mass wherever we want, but we also have to be careful that we're not obstructing the airflow, because having any obstructions in the airflow will create weird oscillations and also will just affect the performance of the flight. It will reduce the flight time because the motors are having to work harder. So you can see from this top view, the propellers are mostly unobstructed by the chassis. We made sure that no components were directly in the way. Everything is as close to center as possible. Now we could also make this overall size a bit smaller, but then we would start obstructing the flow of each of the propellers. Now the circles that you see around the propellers are just the path to make sure that we understand the full sweep. And these are 5-inch by 4.5 pitch props. So this is the final size that we're going to go with, and we have a good idea of how everything was designed to make sure that we're not restricting that. Another thing to consider just from a pure mechanical standpoint is the direction. So when we're talking about the direction, you'll notice that the motors are all spinning toward the center of the chassis. Now the direction again is important because we have to worry about obstructions. But in addition to the direction they're rotating, the proximity to other objects as well as the proximity to other propellers can greatly affect the performance as well as increase the noise that a quadcopter makes during flight. These are all things that we need to take into consideration as we're designing our quadcopter. We want to reduce the number of obstructions around the propeller. We want to make sure that the chassis itself or the airframe is rigid. And we also want to make sure that we're not restricting the amount of thrust that we're applying. Now this is one reason for flipping the motors over and reversing them and trying to keep them away from the body as much as possible while allowing as much airflow to go through as possible as well. In this lesson, we'll focus on creating battery keep-out sketches. After completing this lesson, you'll be able to create a sketch, create a constraint, and create a dimension. Welcome to the part in our course where we start to design our own quadcopter. Now, if you followed along this far, you've been given a lot of different information and you're probably ready to get started. But there's one more thing that we want to take care of first. You want to make sure that you make a new project folder, and I like to make subfolders. So in this section, we're going to be talking mainly about the role of a designer, making the shape, the geometry, the overall product that we want. So I have a Coursera drone project folder and I have a designer subfolder. That's where I'm going to be placing my files. So now let's go ahead and get started with a new untitled document. So we're starting with a complete blank slate, and this gives us the freedom to do a few things. The first thing that we have to think about is what our end product is going to be. Obviously we know that this is going to be a quadcopter or a camera drone, but ultimately when you're starting a new project you have to think about a few things. In Fusion you have a lot of flexibility. Now sometimes you want to create stuff that's just made out of bodies. There are no moving parts or multiple components, so you can just get started modeling. In our case, we're actually going to be creating a quadcopter body. We're going to add a bunch of components like the motors, the batteries, and all the other components that are needed. So before I get started with my first sketch, I want to create a new component. So for my Assemble tab, I'm going to click this icon with the plus on it to create a new empty component. We want to go ahead and rename the component, and this is an important part of the process. The name of this component is going to be the body of our quadcopter. Now you can call yours whatever you like. It really doesn't matter. It's ultimately up to you. But I'm actually going to name mine X Star. Now the reason I'm using that name is because it stands for X as in the shape, and star stands for search, terrain, and return. So ultimately this thing is going to come back, even though we have a live video stream. But that's where this name came up from. But go ahead and create your own name or use this name if you wish. But this name in this component is going to signify the body that we're going to be creating. Also notice that I have it set to activate, so it'll automatically select the radio button next to it, and we're currently working inside of this component. We can expand it and we can see the origin, we can see the axes as well as all the planes. Now for us, we want to get started by sketching on the top plane, which is the XZ plane. So you can do this in a few ways, and we've already been through the basics in this course, so I'm really not going to focus too much on all the ins and outs of starting sketches and how to access some of the tools. So feel free to use your own methodology. Generally I like to click sketch first and then I select the plane on the screen, and that's how I usually get my sketches started. We have our overall design criteria. There's a few things that we need to make sure that we fall within. We want to keep it as small as possible, obviously, and a lot of the other design criteria really come down to component selection. So the first sketch that I want to create is going to be my keep out sketch. And what I mean by that is there are critical components that I want to make sure can fit within this design. Now ultimately with a quadcopter, the design is going to be based on the batteries, right? Because we have several different battery options that we want to choose from, and ultimately the motor and propeller size and location. We're not quite to the location of the motors just yet, but I want to start by creating a top-down sketch of my batteries, and that way I understand where the batteries are, where they're going to be located, and what kind of space they take up. So we're going to start with a rectangle, and I like to use a center point rectangle, and I'm going to draw it over here to the left and just place it and zoom out a little bit. then I'll hit escape on the keyboard to get off the rectangle tool. Now you might be wondering why I did this, why I chose to just sketch it off to the left. Well, I'm going to take this right line and select it, Control select the origin, and then I want to place a midpoint constraint. So that's going to make sure that this line here is directly centered on my origin. Now this is important because if you'll remember from our design criteria, we're going to be using 2 batteries no matter which size we choose, and we want to make sure that the mass of those batteries, which is 50 to 65% of the overall mass, is centered on the device, centered on the quadcopter. So by making sure that this line right here has a midpoint relation with the origin, we know that we can start basing our design off of that origin and make sure that everything is symmetric about it. The next thing that we want to do is we want to place some dimensions. Now I'm going to hit D on the keyboard to place my dimensions, but again you can access that tool however you like. The first battery that we're going to be dealing with is going to be that 1500 milliamp 3S. So I'm going to place this width dimension of 33.5, and I'm going to place a height dimension of 75. Now this is the smallest battery that we dealt with. So this one's going to give us a pretty good thrust ratio, but we're going to have about a 10-minute flight time with it. The other battery that we wanted to deal with, or some of the other batteries, went all the way up into the larger 4S range. Now, during the design criteria, during the calculations that we did, figuring out what a jump in batteries would do for us, we realized that the larger capacity 4S battery would give us better thrust while drawing less current and allowing us to get a longer flight time. So while this battery is great, and this is where we're starting at, not only because it's a very inexpensive battery, but also because, again, it's smaller, it's easier to deal with, but we also want to make sure that we plan for a larger battery. Now, we have to think about the entire process here, and so this is the important thing of this course, is we're not just going step by step showing you how to model this so that you have the end result. We want to make sure that you understand the process, everything that we go through to design something, to make sure that you can make those decisions on the fly whenever you're designing your own products. So in our case, we have to sort of weigh the pros and cons of these designs. Now yes, ideally the 4S battery with the larger capacity is great, but it's actually very big. It's fairly long, which means that it's going to create some issues. We're going to have to make the overall size of the design bigger than initially intended. So we really need to make the decision if making it larger to have a little bit longer flight time is going to be more ideal, or making it smaller and reducing the flight time by a minute or 2 is going to be a better option. So to get started, I'm going to draw an intermediate option, a 4-cell battery that has 2200 milliamp hours. So it's a little bit smaller than the one that we talked about in the course, but it's small enough that we don't have to change the overall size of the design because it fits within the criteria that I'm looking for. Now you might be wondering how I know that. Well, I know that because I've already played with all the numbers and I understand the differences. This is a great exercise for you to do, to draw all the various batteries that you want to play with and figure out how they fit. So I'm going to draw this one on the right side. Again, I'm going to make sure that I have a midpoint relation. So I'm going to select my line, Control select the origin, and place that midpoint relation. Then D on the keyboard. And for the 4-cell 2200 milliamp hour battery, it's actually 34 by 34 square, and its length is 105 millimeters. So you can see it's not that much bigger than the 3-cell that we're dealing with. It's a little bit longer to account for that extra cell inside of it. But in terms of the width, it's only 0.5 millimeter wider. Now the great thing here too is that the extra height or the extra thickness in this one actually comes from the height of the battery. It's 34 by 34. Where the 1500 milliamp is actually not a square shape. It's 33.5, and then it's a little bit thinner in the other direction. But we're accounting for all these numbers, and this 4-cell 2200 milliamp hour battery is going to give us the thrust that we need. It's going to have a fairly good thrust ratio. It's not that heavy. It's not as heavy as the 2650 milliamp hour battery. And more importantly, it's going to fit within roughly the same criteria, the same size. So we don't have to make the overall device bigger. So now these give me a good idea of sort of the range of battery that I want to deal with. Of course, there are probably hundreds of different batteries on the market, and you could spend hours and hours going through all of them, figuring out which one is best. And that's actually a really good idea, a really good practice. And if you go through that, you want to make sure that you not only find a battery that fits in terms of size, but one that also is a very common battery. You don't want to find some random manufacturer that can produce this perfect size battery, but you might not be able to get them very easily, or they might just not be available at all. So make sure you stick with a reputable brand, one that has multiple sizes on the market, and make sure that you always have some options. We're designing all of our products to be configurable, so we can change the size, we can make adjustments, we can make new 3D prints, and we can make use of these different sizes. So this is the main portion of our Keep Out sketch. So we're going to stop this. We're going to expand the Sketches folder. We're going to click on it twice, and we're going to call this Keep Out. So now we have our Keep Out sketch. It's a good time to go ahead and save the file so we don't lose anything. And notice that my location is the Coursera drone project and inside of the subfolder Designer. So again, you can call this design whatever you want, and it's probably a good idea to spend a little time thinking about it. I'm going to call mine the X Star. And I'm also going to make sure that I save it, make sure that it's in that location. So I'll expand my data panel, make sure that it's there. And now we're good to go and move on to adding some more sketches. In this lesson, we'll talk about how to start a complex part. After completing this lesson, you'll be able to create construction geometry. With our battery Keep Out sketch in place, we can make sure that we're currently dealing with an active component, so any new sketches that we create will be placed inside of it, and we can start to lay out the sketches for the overall shape of our design. Now you might be wondering why we don't have more Keep Out sketches. Most of the components are quite a bit smaller than the batteries. The batteries are not only the greatest in terms of the amount of mass that they add to the overall design, but they also have the biggest size. Things like the power distribution board, or the receiver from the transmitter, or the camera itself are all quite a bit smaller. Most of those components are actually going to be stacked on top of the batteries. Not necessarily directly, but in terms of how everything's going to be mounted. We're going to have our power distribution board on top. We're going to have our flight controller directly centered on the origin, and it's going to be on top of everything. And we're also going to be able to place our receiver from the controller. Also, our camera is going to be located on the front of the device, and the transmit antenna will be on the back. So all these various components, including the speed controllers, are all going to be stacked in a way where they're not really going to be affecting the performance of the overall quadcopter. Now things like the motor and the propeller, those are obviously pretty critical components in terms of their mass, but they are going to be at a fixed location. We're not going to be moving them around. Everything else does have mass, but it's quite a bit smaller than the batteries. So we are free to sort of move them forward or backward to make sure that they're not obstructing any airflow or in the way of the propellers. So that's why we're really just focused on the batteries. Now ideally, if you knew exactly which battery you wanted, you would just draw both of those on left and right. You would create a mirror. But in terms of my design, I want to make sure that I account for both of those. So now that we have the battery Keep Out sketch, I'm going to rotate a little bit, and I want to create a sketch on the front plane. So again, I like to start my sketches by selecting the new sketch, and it gives me a good idea of the plane I'm dealing with. If you're ever curious about the plane, when you hover over it, you notice that it highlights it in the browser. So we're dealing with plane XY. And if you look at the view cube, you can see that we're also dealing with the front plane when we select XY. So that can sometimes help. So for this front sketch, what I want to do is I want to create the shape of the new drone from the front. Now this is not the full solid shape because obviously it's going to be a very complicated part, but I'm going to create a reference surface that's going to give me the top shape. Now we're keeping this fairly simplified because we want to make sure that we explore a lot of creative geometry. We want to make sure that we learn a lot of the advanced tools as well as how to apply some of the basic tools. So you don't necessarily have to 100% follow along with what I'm doing, but it's a good idea, especially if you're new to Fusion and you're new to designing, that you follow pretty closely along with what I'm doing so that you don't get too far away from the original core aspects that we're trying to learn. So the first thing that I want to do is start a line, And again, you have many options for how you can get these tools. You can use the marking menu, you can go to the sketch option, and once you're on the sketch option here, you can go directly to the line tool, which is at the 6 o'clock position. So if you want to do this fast, you just hold down the right mouse button and drag straight down, and you're on the line tool. You can also hit L on the keyboard to hit the line tool, or you can use it directly from the top toolbar. All right, so again, I like to access these with quick keys or various ways, so I'm going to use the marking menu to access my line tool, start at the origin, and I'm going to draw a line vertically. I'm going to click, and then I'm going to hit the green check mark. I want to hit escape to get off of that line tool, and I want to take a look at something. It automatically applied a vertical constraint for me, but the line is still free to float around. There are two things that I need to do with this. First, I need to select the line by left clicking, and then I'm going to make this a construction line. It's only there for reference. The next thing I want to do is press D on the keyboard, and I want to dimension this line. And this one's going to be 76.2 millimeters, and I'm going to zoom out. Go ahead and draw one more line. This one is going to be from the point at the top to the left, but I want to make a note here. So we made this a construction line after the fact. If you know that you're going to be sketching construction lines, you can turn the construction option on, and then everything you sketch will automatically be a construction line. Just remember to turn it back off when you want to create normal geometry. This line does not need a dimension. It's only here for a tangency reference. But notice that it automatically applied a perpendicular constraint. So now we have perpendicular constraint, the points are coincident, and I have a vertical reference here. You might be wondering where 76.2 millimeters came from. Well, if you remember from our design criteria, we wanted to keep the entire device as low profile as possible. Most of the camera drones on the market are relatively tall for additional flight stability, but we're looking for making an extremely agile craft, but we wanted to keep it as low as possible. So 76.2 millimeters is 3 inches, and 3 inches is sort of a criteria that I gave that I want to try to fit into. Now, of course, we could make it taller or smaller as needed, but 3 inches will give us a pretty good margin of error in terms of keeping enough air above and below the props, so that way we don't have any restrictions or prop wash or any weird oscillations when we're trying to take off. So that's the starting point, and that's where that 76.2 came from. Again, when you start these designs, sometimes you have to give yourself artificial criteria and see how things fit. And if we find out that 76.2 is too much or not enough, we can always come back to this sketch and adjust it, and everything else will be based off of that number. So as we look at this, 76.2, this is our starting point for the center line of our front shape. So we're going to create an arc by going up to Sketch, and we're going to create a tangent arc. Now the reason we're going to create a tangent arc is because we're going to carry tangency from this horizontal line, and we're going to carry it out to the right. Now if you like to design out to the left, that's perfectly fine. I prefer to design out to the right. So I'm going to be starting from here and simply drag that out and then hit escape. Automatically have tangency applied because of the type of arc that we used. And now there are two more dimensions that we need to apply to this. So D on the keyboard, we're going to go from this endpoint, from the origin, or from this vertical line. Either one is going to be fine. And we want to place a horizontal dimension of 200 millimeters. Then we want to give this a radius value of 500 millimeters. Now again, you might be wondering where these numbers actually came from. The 200 millimeters is because I want to fit within a certain constrained overall size. Now remember, we're dealing with half of the shape here. So from the front, we have 200 millimeters wide, and it's going to be wider than our overall design. And the radius value is just approximately what looks okay. We want a little bit of curve because we're dealing with a 3D printed plastic part. If we print it flat, it's not going to be very strong. That little bit of curvature is going to give us some extra strength, some extra structure. So the 500 doesn't really matter here. It could be more, it could be less. It really just gives us a little bit of rigidity to the overall design. Now if you make that number smaller, you could push the motor up higher and not have to worry as much about prop clearance. If you make the number smaller, you're going to have more curvature there, and then you're actually going to restrict where the propellers can go because you're going to start to run into issues where the propeller might hit the design. So again, somewhat arbitrary numbers, just making sure that they're visually okay and making sure that that 200 is bigger than what we want to design, because ultimately we're going to trim this back. So let's go ahead and stop the sketch. And again, I want to rename this sketch, and I'm going to call this front profile. Let's go ahead and save our design. And if you want to add a version description, this will be visible on Fusion Team. But for right now, I'm going to leave user saved and just say OK, so we can start to add some more sketches. In this lesson, we'll talk about creating a top-down view sketch. After completing this lesson, you'll be able to create construction geometry. Let's carry on with our design by starting a new sketch on the top plane. So far we have our front shape, and we also have keepouts for our batteries. So let's go ahead and start a new sketch, make sure that we're on the top plane, and let's start to talk about the overall shape of our design. Now this is where we're really going into more of our mass location and our overall size. So we need to consider a few things here. First thing we need to consider is symmetry. All right, so we need to make sure that the location of our motors, all four, are symmetric about the origin. Now that's not necessarily the case in all designs, but for us it's going to be important to keep all the motors in the right location. We're going to know exactly where our flight controller needs to be to keep it centered, to make sure that we have the most stable flight possible. So we're going to start with a rectangle. I'm going to make sure it's a center point rectangle from the origin, and I want to draw this out. I'm not going to give it any dimensions just yet. I'm just going to place it, and I'm going to turn each of these lines into construction. Now the reason I'm doing this is because this is going to be a square, and this square is going to dictate the location of all four motors. So we're going to come in here and we're going to take this vertical line, control select a horizontal line, and we're going to make them equal. Now this is going to mean that we have a square. Now we simply have to dimension it. Now I've played around with this quite a bit, so I have a few numbers that I want to deal with. So I'm going to be using 265 millimeters from corner to corner. Now when you talk about quadcopters, if you're completely new to this topic, you'll see a lot of people talk about a 250 series quad or a micro quad or different sized quads. Well, the 250 is generally the size between the motors. So when we're talking about the size of the quad that we're building, we're looking at about a 250 size quad, a little bit bigger because we want to incorporate two batteries, where most of these 250 size race quads are going to just have a single battery. So we're sort of bumping those dimensions out a little bit, but overall we're going to try to stick between 265 as the smallest number that we can hit. If we have to go bigger, then we can, but this is going to be our starting point. So now we've turned this into a complete construction square. We have a fully defined square because we have an equal relation between a vertical line and a horizontal line, and we have a dimension from corner to corner. Now I want to start to place a bit more information here so we can start to really visualize the overall shape. So the first thing that I want to do is I want to draw a circle in this bottom corner. And again, you can access these tools however you want. I'm going to use my quick keys on the keyboard, the letter C, and I'm going to place a circle here that is 28 millimeter diameter. Now this is going to be the outside diameter of my motor. Now if you remember when we talked about our design criteria and the motor numbers, we're dealing with a 2205 motor, which is 22 millimeter diameter on the stator and 5 millimeters tall on the stator. Now the overall size of the motor itself is 28 millimeters on the outside. So this gives me a good flat circle area that I can mount the motor, knowing that it's exactly the size of my motor, and I'm not going to be obstructing the props at all. Because I don't really need this circle, I'm going to turn it into construction as well. Now I don't necessarily have to put this on all four corners, but visually if it helps you, you can certainly add another one to any of the corners, especially since we're dealing with two different size batteries. That could potentially help. Now because I know that the width of these two batteries is essentially the same and this one's taller, I know if it's going to clear on this side, it'll clear on this side just fine. Next I'm going to place another circle, and this time I'm going to do 127 millimeters. Now this is going to be the outside diameter of the prop that we're dealing with. So we're going to be dealing with a 5 by 4.5 pitch prop. So this is the overall spin or the overall circle that this prop is going to be moving in. Now again, this can be construction. We don't need it to be any geometry that we're going to extrude or anything like that. But this gives me a good reference for the location of my battery and the location of the prop. Now also keep in mind that we're looking at everything in 2D right now, and that's something that's hard to sort of get around at this stage since we don't have any geometry. So this is assuming that the thrust plane, or the plane that the actual prop is spinning on, is also centered on the mass of the battery. All right, remember, so that was sort of important. That was a topic we talked about in terms of where the center of gravity vertically is going to be. If we move the weight down below the props, then we're going to have more stable flight, but it's going to be a little bit harder to change directions. If we have it completely centered on the thrust plane, then it's going to be really quick at changing directions. It's going to be really agile in the air. If we put it above, then it's going to be very easy for it to flip and do some of those acrobatic maneuvers, but it's not going to be as stable in flight. All right, so again, this is why you see a lot of off-the-shelf camera drones that are meant for photography or video. You see that they'll have the props all the way at the top and all of the masses below the props. And that's because they're not necessarily meant to be agile. They're not meant to be a quick sort of flying drone. They're meant to be very stable in the air to give you good control over the camera. All right, so keep that in mind that the location of the mass as we're looking at it, we're only really talking about up and down, left and right in a plane. We're not talking about going vertically in 3D just yet. But assuming everything clears from this view, then we have complete control over the height of the batteries. Now, if you're planning on putting them well below or well above, then of course we could tighten everything up a bit more. But I found that this 265 millimeter number between corners is going to be about the extent that we can go. Now, if you decide in your design that you want to use a much larger battery, a much longer battery, for instance, the 2650 milliamp hour battery that we talked about in our design criteria, then you're going to have to go a bit bigger than 265. You're going to have to push these motors out a little bit because you can see that this one here is going to be fairly close. We're going to get pretty close to the prop, and that's about as close as I would feel comfortable. This one is 105 millimeters long, whereas the larger 4-cell battery was 137 millimeters long. So keep that in mind that if you decide throughout your design that you want to use a bigger battery and you want to fly this thing for as long as possible, then you're going to have to make the overall size a little bit bigger. One thing that we haven't talked about in the design criteria and that could potentially be important to you is the actual production of the body. Now, assuming that you have access to a 3D printer wherever you are, the type of printer that you have access to, as well as the size that it can print, is going to be important to you. Now, a lot of printers, for instance, a 3D printer that's a desktop unit like a MakerBot Replicator, which is on the higher end, the higher scale end of a desktop unit, that's going to have about a 12 by 12 inch print table. All right, so keep in mind that if you're designing for a specific printer, then you want to keep that in mind as well in terms of the size. Now, we're doing everything as if this body is one piece. Of course, you could make it multiple pieces and bolt it together or whatever the case might be. We're assuming that it's all one piece, and we're going for an SLS nylon print. So one big 3D print for our design. But that might change depending on what you're designing for as well. So now that we have a single prop and a single motor in the location, I want to start to lay out what the shape of this thing is going to look like. So I need to add a few more lines. And the first couple lines I'm going to add are construction. So I'm going to turn on construction, use my marking menu, start the line tool, and I'm going to be coming out collinear here. I'm not going to add any dimensions just yet. I'm going to hit the OK. I'm going to go from the origin out to the right, again not adding any dimensions just yet, and I'm going to say OK there. And then I'm going to add a vertical line, and I'm going to add it off to the right for right now, and I'm going to say OK. Then I'm going to hit escape. Now this vertical line I'm going to select, control select the origin, and I want to place a midpoint constraint. All right, I'm going to hit escape, and that way this line it's constrained to the origin at its midpoint, so I can move it up and down and make sure everything is symmetric front to back. I also have this horizontal line, which is going to be the location of the mirror from left to right or front to back, depending on how you're looking at it. And I'm going to go ahead and I'm going to turn off the keep out. I'm going to turn off the front profile. I don't need to see any of those right now, especially the front profile. It's not doing anything for me. But now what we've done is we've laid out some symmetry lines for left to right, because we're only going to be sketching everything on the right-hand side, and front to back or top to bottom, again, depending on how you're looking at it and visualizing it. So let's get started again with the line tool. I'm going to start sketching out to the right, and notice that it's still construction because I didn't turn that construction off. So that's something that you want to make sure you do. Go back again and turn that construction off before you start sketching. So we're going to come out to the right. We're going to come over here. We're going to draw a line, and I'm going to make sure that I'm not creating any constraints. So I'm going to hold down the control key. Holding down that control key will override any persistent constraints. I'm going to let it go and snap to this point. And this is going to be all that I need to sketch so far. I want to take this line out right here, and I'm going to control select this line, and I'm going to add a midpoint. I then want to make sure that I add a perpendicular constraint. Might have to zoom in between these two. So now I have a perpendicular constraint between this line and this line. It's midpoint, and this line is collinear with that X, that cross that's going directly through my origin. Now I just need to add a few dimensions. So the first thing that I want to do is press D on the keyboard, and I'm going to add a 50 millimeter dimension here. Now this might look kind of funny right now, but once we start to add a bit more dimensions, it'll make sense. Again, we're going to place another dimension, and this time instead of placing something here, I'm going to click on this 50 and hit enter. So what this does is it makes that number equal to this 50 millimeters. So that way if I decide to come back and change this 50 to a 75, it's going to update both of them. Now while that works out great in this instance, it may or may not work out great in other instances. So just keep that in mind, that creating this equation, this reference on the fly, can be very helpful, especially when you're dealing with symmetry and you're dealing with an instance like this where you're trying to keep everything as symmetric and uniform as possible. I'm going to add a few more dimensions in here. I want 105 degrees on this angle here, and this line I'm going to make 100 millimeters. So the last thing that really needs a dimension is going to be this line right here, and I'm going to make this 30 millimeters. So again, you might wonder where these numbers came from. Well, as we're looking at this, the prop is 5 inches, and it's spinning all the way out past where we drew. Now this doesn't necessarily mean that our prop is going to extend past our body, but the overall shape that we drew from the front is going to be the overall shape of the top of this quadcopter. That doesn't include anything that goes around the blades to protect them or anything like that. So this is why I wanted to stop short, so that I can really focus on the design of the area that goes around the prop and protects it. So I'm stopping there at 50 millimeters within the 5-inch prop circle. The 30 millimeters up here is going to stop short of that 5-inch prop. Now I could make it coincident with here, and it would be pretty close to 30 millimeters. But essentially this is going to give me a vertical line, and I can actually draw that vertical line here if I want to. That's going to allow me to keep an area for my components, things like my camera, my flight controller, and all that, and allow me to keep that squared off. And that way I can have solid geometry here if I need it that's not obstructing the flow of the prop. All right, so we got a good bit drawn in, but now we need to start to add some mirror and some symmetry. So let's go ahead and stop the sketch for right now, and let's go ahead and save our design, so that way we can come back to this sketch and make edits without losing any of our work. In this lesson, we'll go over detailing a top-down view sketch. After completing this lesson, you'll be able to create a sketch mirror and create a sketch offset. Since we've hopped out of the top-down sketch, let's go ahead and let's just rename it. I'm going to call it top-down shape. And again, you don't have to follow exactly along with what I'm doing, my naming conventions, or even naming the sketches if you really don't want to. This is the design process that helps me as I'm going through. And this is really because once you get a dozen or more sketches, which we're going to have quite a few more than that, it makes it a lot easier for you to come back to the browser and figure out what each sketch was. Sometimes you might decide to do the keep out sketches first. Sometimes they might be fifth in line. You might have some geometry first and so on. When we look down here at the bottom, also when you hover over the sketches in the timeline, you can see exactly which component it belongs to and exactly what the name of that is. So we're going to double click on the top-down shape, we're going to edit, and we're going to start to add some mirrors. So under the sketch drop-down, we want to go down to mirror, and the objects that we want to select are going to be the solid lines as well as this 30, and we're going to mirror about this horizontal line. If we zoom out a little bit, go ahead and say OK. So now what we've done is we've created half of the design. Now remember, we're only drawing half of it and we're going to mirror it to the other side. It really helps out with symmetry because you know with 100% certainty that everything on the right side is going to be the same as everything on the left side, at least until there's some unique feature that has to cross over. We're also going to take this vertical line and we're going to change it from construction, we're going to change it back to a normal geometry. So now we have everything on the right hand side that we need to start creating the shape. At this point in time, I'm going to go ahead and stop the sketch, and notice that this line extended past because it wasn't part of that symmetry, it wasn't part of that mirror. Sometimes it's hard to see when you're in the sketch, so sometimes it can be helpful to exit the sketch and then you can come back and you can drag it into place and have it snap to that geometry. Now when we stop the sketch, it makes a little bit more sense. There are a lot more elements that we need to add in, but at this point in time, I'm going to break them out into different sketches. Now the reason I like to do that is because when I go back to make edits or when I go back to make changes, sometimes it can get overwhelming to see dozens and dozens of constraints and dimensions and all those things. So it really helps me to come back after the fact in a separate sketch and just project geometry as needed. So let's start a new sketch, again on the top plane. We're going to select XZ. And now what we want to do is we want to start to create some of the offsets because obviously we're not going to make this just one big solid body. We're trying to keep the structure as minimal as possible to keep it light, but also keep it as strong as possible. And I know that's a little bit tough to do, so we're going to take a look at how we can achieve this. So with this profile, we have a few things going. We have a complete closed profile here, and we have a complete closed profile here as well. We also have some reference lines for where some structure is going to be. And we potentially have sort of a layout of where we need openings or where we want to minimize the restrictions to let as much airflow through as possible. So let's start by taking this outside profile and we're going to offset it 10 millimeters. So I'm going to go around and rather than use the whole profile, I'm going to grab what I want and I'm going to use my marking menu and we're going to offset this 10 millimeters. I'm going to type in 10 and I'm going to say OK. Now notice that I didn't chain the selection, and if I come back and I turn off the top-down shape, notice that I don't actually see anything here. So I'm in this new sketch, but my offset is actually not in this sketch. So if we go back to the top-down shape, notice that the offset is actually in this sketch here. So this is something that we need to be aware of. So I'm going to undo back before that offset, and we're going to look at how we can bring this information into the current sketch. So in order to do this, we're currently editing sketch 5. Under our sketch dropdown, we have project include and project, which is the letter P. So this will allow me to bring in information that I want to have in this sketch. I'm going to go ahead and bring the center line in as well, and I want to bring this line in as well and say OK. I'm also going to go ahead and draw circles here as well as here. I'm going to make both of these equal to each other. And then I want to give them a dimension. Now, I don't want them to be exactly what the prop is. I actually want them to be just a little bit bigger. So I'm going to give it a dimension between these of 2 millimeters. Now the reason I did this is because this line is going to be where a support is going to be located. So I don't want it to be exactly 5. I want it to be a little bit bigger so I have enough room. And this isn't going to be directly in contact with the propeller, but it's going to be above it. So that way I know that I'm not obstructing the airflow, or at least as minimally as possible, while still giving it structure. So now if we hide the top-down shape, notice that we have the offset, and anything that we projected, for instance, I added a dimension from here to here, it automatically projected that into my sketch. So now what we're dealing with is a complete copy of some of the shapes in the top-down, with the exception of not looking directly at some of the construction geometry that we had. So this helps clean up a bit what we're looking at and helps make our offsets more realistic. So again, I'm going to use my marking menu for offset, and if you select chain selection, it'll only carry as long as there's tangency. But what you want to do is you want to select all the entities that you want to offset, and I'm going to bring these in 10 millimeters and say OK. I'm also going to place a circle at the center here. That's 28 millimeters. And I'll do the same thing over here. And I'll make these equal. Now the reason I didn't project this specific circle is because I don't necessarily want to drive it off the 28 that's in the first sketch. I might want to make it bigger or smaller. This is going to be the mounting circle for our motor, which has a 19 millimeter diameter bolt circle. Now all this information is directly from the DYS manufacturer's website, or you can find it on various websites. Wherever you find the motor for sale, generally that information will be located there. Now there are a few more things that we want to add in here. I'm going to start by sketching a line from the center of the motor to the origin and back up to this one. So this is going to be the location of a support. It's going to allow me to add some structure to where the motor is supported. And of course the motor actually needs to be supported by these walls as well. We also want to add a bit more. We're going to go from here down to here. And we're going to eventually add some structure inside of this center as well. So for right now, as we look at this, we've got the motor floating out in space. We've got these 10 millimeter thick walls on the outside. And we need to start adding, again, some additional thickness. So I'm going to take these lines and this line, and I want to offset those as well. So again, using offset, I'm going to grab both of those lines, and I'm going to offset them 5 millimeters. And we're going to go -5. And we're going to repeat it, again, using the marking menu. And this time I'm going to offset them +5. Now keep in mind this extends out, but I don't need to use this. The selection process inside Fusion, when we go to do things like extrudes, it's very simple, so I don't need to worry about trimming this geometry. And oftentimes, if you go to trim geometry, what will happen is it's going to undo some of those dimensions and constraints. So oftentimes it's better to just leave it in there. Now one thing I also like to do is I'm going to take this number here, and I'm just going to click on this one and say OK. So that way the offset is controlled completely by this one here. So if I change this offset to 6, it'll change the other one as well. So a very easy way for us to make sure that we keep those dimensions in check. We can also do that with this 10 millimeter and just say that this 5 is half of the 10 if you want. So there are various ways that we can do this. Now again, we've got some progress. As you're learning Fusion, or as you're starting to get into this, it's a good idea if your sketch is going to be very detailed, if you're going to have to add a lot of information, to go ahead and stop the sketch and save the file. So that way you always have a point that you can come back to. Now let's say that you get pretty deep into the sketch and you decide that you don't like it and you want to start to undo it. Well, if you've exited the sketch and saved it, then you have a version of the file, in this case version 4, that has that sketch. And if you save a later version with the more complicated sketch, you can always go back to that version as well. So it's pretty flexible, and I encourage you to save often, so that way you have various versions that you can reference if needed. In this lesson, we'll complete a top-down view sketch. After completing this lesson, you'll be able to create a sketch mirror, create a link dimension, and create a projection. So let's go ahead and rename the sketch while we're out. I'm going to call this top-down cut, and then I want to go back and edit the sketch. So from this sketch, we've got our 10 millimeter outside wall. We still need to add some offset to this line, and we need to add a bit more information in various areas. We need to add some offsets on the inside as well. So let's go ahead and add a bit more detail. So I'm going to do an offset of this line, and we're going to say that this dimension is 5 millimeters. Now you'll notice that while I'm inside of this operation, it doesn't let me click this. So I'm going to go ahead and just say 5, then I'll double click on it. Sometimes it helps if the constraints are in the way to hide the constraints. And let's go ahead and do another offset. We can say -5, and again we can make it equal. Now one thing you'll notice when we offset a line is because this line ends at a point, what we're actually doing is we're creating a shorter version. Now again, trim or extend, if we use this, it's going to undo that dimension. And you can see that it takes it away. And that's actually okay, but it also undid some additional dimensions. So the way to get around this is, instead of using that offset, is to simply just draw a horizontal line. Now if the line doesn't happen to be horizontal, you can make it parallel, or you can do some additional constraints to make sure that that works. But in our case, they're perpendicular to this vertical line, or a horizontal would be just fine. I'm going to make this one construction, and any center line that I don't need, I'm going to make those construction as well, and that helps with the selection process down the road. Then I want to apply a dimension. So in this case, because I'm in the middle of applying a dimension, I can simply just add it there. And also, if you know the dimension, we can simply type in D19, and it'll be equal to that as well. Under Modify, you can go down into Change Parameters, and you can make universal parameters. They're called user parameters, and you can simply name them ahead of time. So for instance, if you wanted a specific 5 or 10 millimeter offset, instead of having it called D19, we could name it offset, and notice that it re-references all of these to be equal to offset. You could make that ahead of time, or you could name it on the fly instead of being D19, and you can do it that way as well. So that way you don't have to remember D19. All right. So for instance, this 10 right here, we can say that this is offset times 2, and that is equal to 10. So that way, if we ever come back and we change this dimension right here, which is currently 5, if we change it to 6, and then this one will equal 12, and so on. So again, it's just a way to make sure that we're keeping those numbers fairly consistent. All right, so now we've got a bit of structure in the center. We've got the structure around the outside. We've got the structure going to the motors. And again, we don't have to worry specifically about trimming this up. If we trim it, then we will lose some of the offset information because of how the offset tool works. But we can simply leave it long because we can still select these areas. So now we want to add a little bit more. So we need to make sure that we have some structure for the motor that comes to these sides here. And the way that we're going to do that is we're going to carry a line from the center that goes completely out. So again, I'm going to start a line. I'm not going to snap to the midpoint. I just want to snap to the line over here. And the way that I'm going to make this work is I'm going to make it coincident, not in a midpoint relation. And then I'm going to make it perpendicular to this line here. All right. So this is a center line. This is where we're starting our structure. And then we're going to carry a line from this point that's parallel out to the side. So we'll find that intersection point, and it snaps to it automatically. And notice that that's coming out perpendicular automatically, and we can take it out to the wall, and we didn't have to add any additional constraints. Now it's a little bit different when we get out here because we don't have anything to snap to, but I'm actually going to take it and drag it out, and it's tangent, and all I have to do is I need to make these parallel, and it'll fully define it for me. So if I temporarily hide the constraints, you can see what we've done is we've added some structure here, and we've added the bulk of this structure here because this is a shorter section. All right, so we're going to have a lot of structure at the center of the quadcopter, and this arm here is quite a bit shorter, so we wanted to carry that structure into the motor as quickly as possible. so it carries it around this corner. And then this one here actually helps provide some additional support to this edge right here. All right, we will be adding some additional structure, so this line, this will be a solid panel area, and this will be a small line here that, that has some structure to it as well. So keep that in mind that this is the reasoning for offsetting this in this one way. Now in general, as we go through our course, we're going to have a section on engineering where we add some more strategic supports. We add some different features to help make sure that this thing is fairly strong. Those types of features will also help us dictate how this thing should work. And again, since I've done this before, I just sort of know that this will work out better and still keep it fairly light. So don't be too worried if you don't understand why some of the design decisions are the way they are. Sometimes it just comes from doing this many times. Sometimes it just comes from experience and so on. We're going to carry on this process on the other side as well. We could mirror this, but sometimes it's just good practice to do it. So if you're new to this and you're new to applying these constraints and dimensions and creating these sketches, it's a good idea to just do it. Just take the repetition as some practice, some experience. So again, find that intersection point. We're going to make these two lines parallel. And then we're going to do the same thing on the back. We're going to come over here. This is tangent, so we're going to make sure that's parallel, and that fully defines it. So that is going to give us some structure for the motor, and it's going to carry that structure right to the center point, and we still need a little bit more. All right, so we're going to have to add a little bit more structure here. We're going to go ahead and we're going to offset this line right here. We're going to not offset this line because we're actually going to leave some of this open in the middle, but we want to carry a line out and we want to offset it in the back so we have a little bit more structure. So I'm going to do this by, first I'm going to draw a line from this to here. I'm going to hit escape. I want to select these two and I want to make them collinear. So what collinear is going to do is it's going to allow me to essentially follow the path of this line without having them connected. So this is going to give me some structure on the backside right here. And we could also just carry it horizontally, but in this case I actually want to keep it going this direction to help with the shape, that X shape that we're going for. So it'll add a little bit more structure to the back as well. And again, using repetition, we're going to follow the same thing up in the front. We're going to use collinear, which we can pre-select if we want to, and we can make these two collinear, and then just make sure that it's deselected once you start modeling again. All right, so at this point, as we're looking at this design, there are a few areas that are going to be open, and there are a few areas that are going to be closed. So this area right here, and this area right here, and this area right there, I'll go ahead and I'll just select them all. All these areas are going to be open. Now this is going to allow the most amount of airflow that we can get without obstructing the prop. Now this area right here is going to be closed off, but it's going to have a minimal thickness sheet right there. So while the majority of this body is probably going to be about 8 to 10 millimeters tall, with some areas that are going to be reduced for weight, obviously. This area right here will probably be 1 to 2 millimeters thick, and it's just for some additional structure. Because of the location of the prop, if we simply just took this brace out and just carried it all the way out here, we would probably have a lot of flex in this area. So we're going to leave some of this up to the engineer and do some simulations and figure out where the weak spots are. But in general, that is the design process for, or at least the thinking behind why these areas are the way they are. Because we have the circle and we want to make sure that the prop itself can pull as much airflow through there so we don't have any obstructions. We're not restricting the amount of airflow. We're not artificially decreasing our flight time because we're having to use more current to try to pull more air, and we're not getting the ideal thrust. And we're carrying the motor back to the center point of the chassis, and we're also carrying it as close as we can to any additional structure. So at this point, that is going to be the majority of the sketch that we're going to need to start to create some solid geometry. So we're going to go ahead and stop the sketch. We're going to make sure that we save our file. And this is going to give us a great foundation to start creating our solid and surface geometry to start to see how this thing will take shape. This is a video overview to accompany written instructions for practice exercise 1. In practice exercise 1, we're going to create a new file with a top-down layout sketch. The sketch will be for a 450 series quad and have 7-inch propellers. This is a video solution for practice exercise 1. To get started, you may want to create a new subfolder in your Coursera drone project file. This way you can keep practice exercises and challenges separate from the normal CAD files. We're going to start with an untitled design and create a new sketch on our top plane. We're going to zoom out a little bit and start by creating a rectangle and a center point orientation. Apply an equal constraint between a vertical and a horizontal edge. Apply a dimension to one of the angled construction lines of 450 millimeters. Next, press C on the keyboard to place a circle at each one of the corner points. Press Escape, select the equal constraint, and make all 4 of the circles equal. Press D on the keyboard, place 7, IN for 7-inch, and all 4 of the circles are now 7-inch diameter. We can stop the sketch and save our file. This is a video overview to accompany written instruction for practice exercise 2. With practice exercise 2, we're going to start an untitled document and create a few user parameters. One for airframe thickness of 8 millimeters and one for offset of 2 millimeters. This is a video solution for practice exercise 2. We're going to start with an untitled document and select Modify, Change Parameters. We're going to select the green check mark to create a new user parameter called airframe thickness. This value is going to be 8 millimeters. Create another user parameter called offset. This one's going to have a value of 2 millimeters. Select OK and save your file. This is a video solution for practice exercise 3. In practice exercise 3, we want to first start by uploading the file C03-W1-PE-03. Once uploaded, go ahead and open the file. Expand the Sketches folder, right-click, and edit Sketch 1. Sketch 1 contains a 2 millimeter offset dimension. We want to double-click this, and we're going to set this equal to a parameter called Sketch Offset. Start typing the letter S, and Sketch Offset user parameter will appear below. Select it and hit Enter on the keyboard. It's now linked, denoted by FX, to a user parameter. Next, we want to modify that user parameter. Under the Modify dialog, select Change Parameters, double-click in the expression box, and set this to 4 millimeters. Select OK, and notice that FX is now set to 4 millimeters. Stop the sketch and save your file.